Okay, chemists, in this lesson we're going to look at how solutes affect solutions. I've broken it down into different types of solutes, specifically solid solutes, liquid solutes, and gaseous solutes, because we need to treat them differently. They do different things. Starting with solids, non-volatile solutes, meaning things like salt and sugar. What they do is they lower the vapor pressure of the resulting solution. So remember, if we plot vapor pressure versus temperature, you get a non-linear increase in vapor pressure as temperature increases. It increases as temperature increases, but non-linearly. That's what the vapor pressure of, let's say, water would look like, or any liquid solvent. Well, when you change it to a solution with a non-volatile solute, at every single temperature, the solution has a lower vapor pressure. So I'll show this dotted line, meaning it still increases non-linearly, but at any given temperature, it's going to be significantly lower. Now, it's not linear, but what is linear is if you plot vapor pressure versus the thing we talked about in the previous lesson, the mole fraction, specifically the mole fraction of the solvent. That is linear, and you get a perfect y equals x straight line as you go from a mole fraction of 0 to a mole fraction of 1, where that would be only the solvent. So I'll even connect those with a dotted line to show that, because what that means is that the mole fraction, if that's 1, then the vapor pressure you're talking about is the vapor pressure of the pure substance, and we use this superscript 0 to mean the pure solvent. And there's a mathematical relationship for this called Raoult's law, named after François-Marie Raoult, and it says that the vapor pressure of a solution, P-vape solution, is equal to the mole fraction of the solvent times the vapor pressure of the solvent, the pure vapor pressure of whatever that solvent is. And it looks like a simple linear relationship, but many times there's a lot of things you have to do to get the mole fraction of the solvent. Maybe turn volume into mass into moles and take the ratio of the two moles, and then you simply multiply it. You can hopefully see how that equation turns into this line as you have more and more solute, then your mole fraction of solvent gets lower, and indeed your vapor pressure gets lower correspondingly. Nice linear relationship. That's one of the main reasons we're going to use mole fraction. And that's it for solid solutes for now. So let's move on to liquid solutes. Liquid solutes also change the vapor pressure, but what we end up getting is a weighted average mixture. When I say a volatile or a liquid solute, I'm talking about organic things like alcohols or acetone. Those are liquids by themselves and therefore a little more volatile. They can evaporate more easily. So they actually have their own vapor pressure to contribute, and you get a weighted average expression of Raoult's law, where the vapor pressure of the mixture is equal to the mole fraction of one component times its pure vapor pressure plus the mole fraction of the other component times its pure vapor pressure. And really, you could think of this as the same thing up above. You could think of this as solvent, except now we have to add solute to it because the solute has its own vapor pressure. You know, we actually had this in the previous equation as well, except the vapor pressure of a solute for a non-volatile solute is essentially 0. The vapor pressure of a non-volatile, almost by definition, is equal to 0. So we only have to consider the solvent's vapor pressure in the original equation. This is just a modified version, and you can see it's a weighted average relationship. This is only true for ideal solutions. Ideal solutions only. And let me show what I mean by that. An ideal solution happens when the molecules interact similarly. So I have some pictures that show what happens when you make a mixture. And we'll start with an example of an ideal solution. These are benzene molecules. and these are toluene molecules. Both are volatile liquids. And when you make a mixture of benzene and toluene in the laboratory, you have to break the IMFs between benzene molecules and break the IMFs between toluene molecules, and then you actually form IMFs between these different molecules. But they're so similar that the ones you break are almost the same as the ones you form. So the IMFs that are broken, IMFs that are broken are essentially the same as the IMFs that are formed. And that's really what an ideal solution is. That's an ideal solution. And that's when we get a weighted average mixture. So what does that look like on a graph? Well, if we plot vapor pressure versus mole fraction, you get the same thing we saw up above. You get a linear relationship, and I'll go all the way across. But that's just for one of the substances. There's going to be a mole fraction of something else as well. I'll actually move this over here and call this substance A. But on top of it, we have some other substance, let's say B, which is just the other component. It's arbitrary if you call one the solute and the other solvent. They're just two components of a mixture. And as we increase the mole fraction of A, its vapor pressure increases. If we just draw a different plot of mole fraction on the same graph, you would also have an increase in vapor pressure, but I'm just going to draw it on the opposite direction for a different scale and point out that it's in fact different than the first one. And what we end up getting when we make a solution is a weighted average between the two. And you get a perfect solid line like that. That's your weighted average. So P-vape weighted average. And that's what that equation up above is meant to illustrate. With this equation, with just one component we have that line, with the other component we have that line, but you combine the two, you get something that's in between the two pure vapor pressures. In fact, that's what those extreme points are. On the left we have pure substance B, and on the right we have pure substance A, and the graph is a weighted average in between those two. That's just for an ideal solution. Now, non-ideal solutions are sort of beyond the scope of AP Chem, but it's worth just looking at them so we can explain why they're a little different, because they're actually really common. A non-ideal solution might be what you get when you mix water with acetone. And I know I just gave acetone as an example of a non-volatile solute, and that's true. It is non-volatile, and you make a mixture with a weighted average vapor pressure, but it's not linear any longer, because this time the IMFs that are broken are actually weaker than IMFs formed. And that's specific for what we call a negative deviation. And what that means is that when you break apart the, let's say, hydrogen bonds between water molecules and the dipole-dipole forces in between the acetone molecules, you're breaking bonds, so you're absorbing energy, but then you form interactions between acetone and water molecules and you release energy. And for those two molecules, it happens to be better in the mixture than when they were separate by themselves. So there's sort of this net release of energy, and it's more favorable to be together, and we see that in the graph. So what I'm going to do is I'm going to first mimic what our pure vapor pressure of the two substances look like. Even though we're not talking benzene and toluene anymore, I'm just going to still plot a similar benchmark for the two. And instead of a linear connection, you actually get a very non-linear depressed vapor pressure. This is the negative deviation. It's actually not just in between the two extreme points, it's even lower at every point still plotted against mole fraction of the different substances from left to right. So there's one other case, and that's the exact opposite of this. Instead of IMFs broken being weaker, it's IMFs being stronger. And that's what happens when we end up having things like pentane and ethanol. Pentane and ethanol are very different molecules, and when they make a mixture, it turns out that the IMFs broken are stronger than the IMFs formed collectively. And that should make sense because these molecules are very different from each other. We have a polar H-bonding ethanol with a very non-polar hydrocarbon of pentane, so they don't really want to mix together. They do, but the interactions that they form are not as good as the collective interactions that they used to have with just each other, frankly, because you're breaking the H-bonding between ethanol molecules is most likely. And what do we call this? This is called a positive deviation. So what we get is, compared to what we started with, we have our reference points here and here. Those are supposed to be linear, and hopefully you already guessed the curve would be sort of above where you expect the linear relationship to be. This is beyond the scope of what you will see on the AP test, but you'll certainly see it in college chemistry classes where you have this positive deviation and also where you have a negative deviation. Usually a negative deviation goes with an exothermic dissolving. So when you mix things, they actually warm up. And the opposite is true when you have a positive deviation. This is an endothermic. An endothermic dissolving. And you can actually detect the temperature changes qualitatively when you mix two liquids. If you mix pentane and ethanol, the mixture actually gets cold because you're breaking more than what you're forming. And vice versa for acetone and water. When you mix the two, it gets warmer because you're forming something that's more favorable than what you broke. And guess what happens when you mix two liquids that are ideal? No temperature change. There's just neither an exotherm nor an endotherm when you mix the two together. Okay, so that's a lot to say about when you mix liquids with each other. The main thing is the weighted average vapor pressure, but these other cases also happen. Let's wrap up this lesson by looking at what happens when we dissolve gases. This is actually the simplest one, and gases dissolve in solutions, and the only thing I want us to know is that the concentration of a dissolved gas, C, is proportional to the pressure of that gas. So I'm going to use C for concentration, K is a constant, and P is the pressure of that gas above the solution. This is how we get gases to dissolve. This is called Henry's Law, named after William Henry, a British chemist, as you can see there. And we're just going to show how it works for a very common dissolved gas, carbon dioxide. So what's the concentration of CO2 at 5 atmospheres of CO2? Well, C is equal to the constant, which happens to be given. It is unique for a gas, so it's 0.031. If you look at that units, that's a molar per atmosphere. I'm actually going to write that way, molar per ATM. And then the pressure is 5.0 ATM, and you get 0.16 molar, and that's roughly what it is in a bottle of a carbonated beverage. But as everyone should know, as soon as you open a beverage that's got carbon dioxide dissolved in it, the pressure decreases substantially. It fizzes, and all that gas comes out of solution. That's because of Henry's Law, because even though it's still carbon dioxide and we still have a gas constant of 0.031 molar per atmosphere, or Henry's Law constant, the pressure of CO2 in the atmosphere is a lot lower. Even though the total pressure in the atmosphere is about 1 atm, there's only 4 times 10⁻⁴ atmospheres of CO2, 0.0004. So you get a much lower concentration at room temperature and room conditions of carbon dioxide. So if a soda bottle is sitting out open in the air, the concentration is far lower than it would be. And that's how they get it to go in solution in the first place. They simply place it under very high pressure of carbon dioxide. Okay, so that's how gases are talked about in terms of being a solute, how liquids can act as solutes, and then how solids act as solutes. We're going to actually wrap this up in the next lesson by looking more at solid solutes and what they do to phase change temperatures.